Hello viewers, today in this part of the discussion we will continue to discuss number system and codes, and the brief outline for today's discussion is as follows. We will start with binary number representation, then we will discuss unsigned and signed representation, then we will go to ones and twos complement representation, then we will discuss twos complement conversion and twos complement arithmetic. Then we will discuss hexadecimal arithmetic and BCD arithmetic, and in the end we will discuss two types of codes, that is gray code and the conversion to binary, and finally we will discuss Hamming code. Binary number representation. So, it can be represented in four different ways, and they are unsigned, signed, which represent basically the magnitude, and the ones and twos complement representation. In case of unsigned magnitude, we can represent only positive binary numbers, but in case of signed magnitude we can represent both positive as well as negative binary numbers. In the other two cases, that is ones and twos complement, also we can represent both positive as well as negative binary numbers. So, in all four representation, positive number is represented in the same way. Unsigned and signed representation. So, let us discuss little bit in detail about them. Since we can only represent positive binary number for unsigned representation, so any negative number cannot be represented by the unsigned representation. For example, if we take 6, then the corresponding binary number is 110, but if we take -6, then it cannot be represented by the unsigned representation. But for signed representation, since both positive and negative binary numbers can be represented, so the magnitude is following a 0 for a positive binary number and 1 for a negative binary number. So, if we take the same example as 6, which is a positive number, then the binary representation is 0 1 1 0, and similarly if we take -6, then the binary representation is 1 1 1 0. So, the first 0 and 1 in 6 and -6 respectively represent the signed bit. 110 for both the numbers represent the magnitude, and so signed bit defines whether the number is a positive number or it is a negative number. Now, the range of signed magnitude is as follows, that is, it starts from minus of 2 to the power of n minus 1 minus 1 to plus 2 to the power of n minus 1 minus 1, where n is the number of variables. So, if we take an example where n is 3, then the range varies from -3 to +3. Similarly, one can identify positive and negative numbers by using sign representation. Now, let us discuss about twos complement representation. The most widely used method of representing binary numbers and performing arithmetic in computer system is twos complement representation. usually one represents numbers in 8 bits or 16 bits depending on the type of computers. The MSB of this represents the sign for the binary number. If it is 0, then it is positive number, and if it is 1, then it represents a negative number. So, the maximum positive number of 2 to the power of n minus 1 and negative number of minus 2 to the power of n minus 1 is possible, where n is the number of bits. Now, let us try to understand the conversion process in 2's complement representation. So, let us convert decimal to 2's complement. So, we can understand this by considering the following example, that is, if we want to convert 35 to 2's complement, then we can follow the steps given below. First, one has to find out the true binary of the number. So, if we take 35, then the true binary of the number is 00100011. Since it is a positive number, so the 2's complement is the binary number itself. So, we can now represent 35 by the following 2's complement number, that is 00100011. Similarly, let us find out the 2's complement of a negative number, and let us consider the example of minus 35 of the decimal number to the 2's complement number. So, the true binary for the number 35 is 00100011. Now, we have to consider 1's complement of the binary number. So, the 1's complement is the complementary number that one can get from the true binary number of 35, and that is 11011100. Now, add 1 to 1's complement such that the number becomes 11011101, and this represents the 2's complement of minus 35, because there is a number 1 at the beginning, and that shows that gives the idea that this represents a negative number. Now, let us convert binary number to decimal number by using 2's complement. So, 2's complement acts as a bridge between the binary number and decimal number. So, let us do that by using the following example, that is converting the binary number 11011101 to decimal number. Since it is a negative number, as we can understand that by following the first bit or the MSB, so we have to follow 2's complement method. Now, complement of this binary number is 00100010. After adding 1, it becomes 00100011, which is the decimal equivalent of 35. Now, let us discuss 2's complement arithmetic. Since we have already discussed the arithmetic operation that goes in digital electronics, we can just start with the first operation, that is addition. So, the addition of two numbers is same as addition of Boolean numbers, and subtraction is done by addition of one positive number and a negative number. For example, if you want to do 8 minus 6 calculation, then it can be represented as 8 plus minus 6. So, one has to take 2's complement for actual binary of 6 and then add with the actual binary of 8, and this will give the binary number for 2. Now, let us discuss hexadecimal arithmetic. 8 and 16 bit computers use hexadecimal number system rather than binary number system, and addition of hexadecimal numbers can be followed by using the steps given below. Add the two hex digit after converting them to decimal number, and if the sum is less than 16, write down the hex corresponding to the hexadecimal number. But if it is more than 16, then subtract 16 and take the carry to the MSB. So, let us try to understand this by using the following two examples. In the first example, we want to represent 9 plus 6, 9 plus C in hexadecimal form. Now, C is represented as 12 in hexadecimal number system. So, 9 plus 12 is 21, which is more than 16. So, if we deduct 16 from 21, we get 5. So, carry 1 to next MSB. So, now 9 plus C will be equal to 15, because 9 plus 5 will be 14, and there is another carry 1 which will be added to give rise to 15. Similarly, we can do 4f plus 2d. Now, f plus 2d is equivalent to 15 plus 13, and that is equal to 28, and since 28 is more than 16, we can deduct 16 from 28, and that gives rise to 12, and it represents C in hexadecimal number system. So, the sum of 4f plus 2d gives rise to 7C. Now, let us discuss BCD arithmetic. Now, because of limitation of BCD, that is the numbers are till 1001, when add numbers more than this number, then we have to check the validity of the number. For BCD addition, follow the steps given below. So, first what we have to do is that add the BCD number as true binary number. So, if the sum is 9, which represents the binary of 1001 or less than 9, it is a valid number and keep it as is. But if the sum is more than 9 and there is a carry out of the MSB, then it is invalid BCD number. Then in that case, add 6 to the result to make it valid, and any carry out will add to the next more significant BCD number. So, let us try to understand this a little bit clearly by using the following two examples. So, we want to add 8 plus 7, and the corresponding binary representations are 1 0 0 0 and 0 1 1 1. Now, if we take the sum of these two numbers, then it gives rise to 1 1 1 1, which is invalid because it is exceeding 1 0 0 1. Now, what we have to do is that add the binary of 6, that is 0 1 1 0 to this number, and hence after addition it becomes 1 0 1 0 1, and now we can write this in a 8 bit digit, that is 0 0 0 1 0 1 0 1, and that represents the BCD representation of 8 plus 7, and that will be equal to 15 in the decimal number system. Similarly, we can do the summation of 52 plus 63, and if we follow the same process, then we can get the BCD number of 0001, 0001, 0101, which is the equivalent of 115 of decimal number system. So, these two examples give us the flavor of BCD arithmetic. So, next we will discuss gray code, and gray code is also called as reflected binary code or RBC, and this name is given after the scientist Frank Gray. So, what happens is that here two successive values differ in only one bit, hence binary numbers are converted to gray code to reduce switching operations. Now, gray code is an unweighted code. So, there is no weighting factors which is used in gray code, and gray code is also called as unit distance code or minimum error code or cyclic code. One can show that the switching operation is reduced in case of gray code. So, let us consider the following example where we convert a binary number to a gray code. So, to do that, let us follow the steps given below. In the first step, we have to record the MSB corresponding to the binary number. So, here in this binary number 1 represents the MSB. In the second step, add the MSB to the next bit and record the sum by neglecting the carry. So, here because we have MSB as 1 and the next number to MSB is 0. So, if we add 1 to 0, then we get the sum of 1 with a carry of 0. Now, in the final step, what we have to do is that we just have to repeat the process that we did in the second step. So, now 0 is added to the next number, that is 1, and finally 1 is added to the next number, that is 1. So, the gray code representation of the binary number 1011 becomes 1110, and here if you observe, then if we consider the next binary number after 1011 and the corresponding gray codes for the two numbers, then we will find that there is only one position where the binaries have changed. That means, instead of changing the binary numbers in more than one place, it is only changing at one place, and hence in this way it is reducing the switching operation. Now, let us discuss gray code to binary conversion. Here also let us consider an example to understand the conversion. Now, let us convert 1110 to the binary number. The first step is to keep the MSB as it is, which is same as when the process that we followed for the conversion of binary to gray code. So, the first bit of gray code is 1, because that represents the MSB. In second step, we have to add MSB to the next bit and record the sum by neglecting the carry. So, now we have MSB as 1 and the next digit is 1. So, if we take the sum of these two numbers, then we will get 0 as the sum and 1 as the carry. And the third step is the repetition of second step. So, now we will add 0 to the next number, that is 1, and that gives us 1, and 1 will be added to 0 and that will give us 1. So, the binary output will be 1 0 1 1. Now, let us discuss a concept called parity. It is a method to detect errors, and a single bit error is detected by this method. So, a signal is a bit of stream along with an extra bit to detect the error. So, if we have a 3-bit number, then we add another bit called as the parity bit, which will detect the error in the signal, digital signal that we obtain. So, this tells us also the number of ones that are there. So, there are two types of parity depending on the number of ones. Either it is a odd parity if the total number of ones are odd, and it is a even parity if the total number of ones are even. For example, the actual signal is 0 0 1 0 and a parity bit 1 is added to the actual signal. Since there are two ones including the parity bit, it is called a even parity. Similarly, if the total number is, or the total number of 1 is odd, then it is called as odd parity. Now, let us discuss a very important coding method called Hamming code. It is a code used to detect errors, and the most commonly used code is a 7-bit Hamming code. For this, there are 4 data bits and 3 parity bits. So, how to arrange these 4 data bits and 3 parity bits in the 7-bit signal that we want to send from the transmission end to the receiver end. So, for that Hamming proposed a method, and for a 7-bit Hamming code, the following is the proposal. Now, let us say for n is equal to 0 1 2 3 till n, the parity bits are positioned in the following places of the 7-bit number. So, 2 to the power of 0 is equal to 1, and that means the first place represents, or first place will be denoted for the parity bit, first parity bit P1. The next one will be 2 to the power of 1, that is equal to 2, and hence the second position is denoted to the parity bit 2, that is P2. Then the next one is 2 to the power of 2, that is equal to 4, and hence the fourth position is denoted to the parity bit P4. And if we had more than 7-bit signal, then the next parity bit would be positioned at 2 to the power of 3, that is at 8. So, the other boxes will be filled by the data bits, and the rules are P1 is dependent on the data bits D3, D5 and D7, and P2 is dependent on D3, D6 and D7, and P4 is dependent on D5, D6 and D7. So, if we are working with even parity, then we can use the following example to understand what should be the parity bits. For example, because P1 is dependent on D3, D5 and D7, if we have D3, D5, D7 as 0, 0 and 1, and if we consider even parity, then in that case P1 has to be 1 to get the even parity, because we have only 1 1 in the data bits. Similarly, P2 will have to be 0 if we have D3, D6, D7 as 0, 1, 1, because we have to maintain the even parity. And finally, P4 is equal to 0 to have the, if we have D5, D6, D7 as 0, 1, 1. So, we found the parity bit of 1, 0, 0 corresponding to the data bits. So, let us try to understand this by using the following example. So, we want to transmit a 4-bit data signal, that is 0, 1, 0, 1, and because this has to be a 7-bit signal at least to send with the parity bits, then we need to find out what should be P1, P2 and P4. So, here D7, D6, D5 and D3 are 0, 1, 0, 1. Since P1 is dependent on D3, D5 and D7, which are 1, 0, 0, so P1 has to be 1. Similarly, P2 and P4 will give us the value of 0 and 1. So, the 7-bit signal with the parity code is now become 0, 1, 0, 1, 1, 0, 1. So, instead of this signal, the receiver gets 1, 1, 0, 1, 1, 0, 1. Then it will look if there is any error in the following way, because the signal that we wanted to send is different than the signal that is going to the receiver. Then what is happening? The process that is happening is that in between the transmitter and the receiver, there is some noise which is included with the signal, which is modifying one or more number of bits. So, that can be found out at the receiver end by calculating the parity bits. So, since P1, P2 and P4 has to match with the data bit, so we have to calculate the corresponding parity bits, and if it does not match, then the signal that is obtained is a incorrect signal at the receiver end. And in this way, Hamming code is very useful for communication of signal from the transmitter to the receiver end. So, viewers, in this lecture whatever we discussed can be summarized in the following few important points. So, we started the discussion with binary number representation, which includes unsigned, signed, ones and twos complement representation. Then we discussed the concept of twos complement method and the conversion involved in there. We also discussed the arithmetic involved in twos complement method. Then a discussion on hexadecimal arithmetic and BCD arithmetic was there. Then finally, we discussed gray code and the conversion to binary numbers, and in the end an important coding method called Hamming coding, which is used for error detection, was discussed. So, viewers, I hope you would have liked today's lectures. Thank you very much.